Hello folks, how are you? Hey, this is a screencast recording that we're doing for today's lecture. I can't be there for forces that have stopped me. The forces of good or evil have stopped me from being there today, but still, I want to come at you with this in this virtual form. So here I am in the future, I think. Anyway, so let's finish up this chapter and start a little bit onto chapter 2 in this lecture and keep on track, okay? So I'm doing the screencast here, and you'll see from time to time I'll be scribbling. So I'll be like doing stuff like this, and I'll be pointing, and it'll seem like I'm doing a lot of scribbling because I'm trying to. If I was there in the lecture hall, I would be pointing with my cursor or with my laser pointer. But sometimes these recordings don't record my mouse pointer positions, so. So sometimes when I'm referring to something and I'm using my mouse to point to things, those don't show up, and that confuses everybody. So I'm going to use my pen here and just point to things that I'm like, hey, this is like wicked important, or like, boo, so sad with the tears going down, or love, you love this. Right? But you'll also notice that my handwriting is not wonderful to begin with, but it's also pretty horrible here because I'm drawing on a tablet, and I am very, very old, and elderly people can't use technology. And so all we do is want our little cup of tea that's steaming hot, and we just want to drink it, and we want to cry with tears, and sometimes we want to definitely eat giant burritos from Chipotle. Anyway, so that's, by the way, a chicken fajita burrito with guacamole and green tomatilla salsa. So I'm sorry, it's lunchtime, and and I shouldn't be recording, so I'm this hungry, but that's just what it is. I'm hungry. I'm a big guy. You've seen this in person, live, right? I just need food. Carbon atom. All right, let's go. Let's do this. All right. So, and you'll also notice too, when I go back and forward between slides after I'm done vandalizing a slide here, vandalizing here, and I go back and forward, you'll see that it erases all my vandalism from one side to the next. So I will be referring to things back and forward because it's the benefit of this, but I will lose the annotation. So but the good thing about it is that you can pause the video here and take notes and do whatever you need to do with it. Okay, so let's just continue. Let's start on this thing. Okay, so let's start right here. Right, ground state of carbon, as we've seen before, is this. Right, it has 1s2, 2s2, 2p, 2 here. Right, there's 1, 2, 3, 4, 5, 6 electrons here because of carbon. It has the atomic number 6, and that's just what it is. That's the number of electrons to deal with. We excite it here using some sort of a reagent or some energy of some sort. Again, this is all a review, right? We've already talked about this already, but I want to just begin because I want to finish up with what we're talking about today, right? The excitation is no matter what it is, it always gives you this excited state of carbon at this point, right? It just bumps up with these 2s electron into the 2p, and it gives you this species over here, right? It gives you this guy over there, these 2p's, right? Now here we have to have some knowledge. I will tell you, please hybridize this, in this case here, to the sp3 hybrid orbital, and hybrid orbitals. And when you do that, you say, okay, sp3 is comprised of 1s orbital and 3p orbitals. When you combine them, this plus this gives you that. Notice the area, like I said before, like we saw in lecture before, that the sp3 hybrid orbital energy level, if you draw a line, it comes in between, the 2p orbital and the 2s orbital. The unhybridized 2p and the unhybridized 2s orbital. So the sp3 hybrid orbitals fall somewhere lesser than 2p and greater than 2s. All right, and so there's that. So that's what I was trying to show you last time in lecture, but I didn't draw it on the same scale. But here it's drawn on the same scale. All right, but remember, you have to be told what to hybridize. All right, so here in this case here is sp3. All right, so that's all that you know from before. All right, so we do that, we hybridize it, and then we get these 4 degenerate sp3 orbitals, and there you are. All right, the 4 degenerate sp3 orbitals here is made of 3 parts p orbital here, right, and 1 part s orbital here, which is why this guy here looks like an elongated p orbital here with one side that's bulbous, because what we did here is that we took one regular p orbital and then we added an s orbital to it, right? And I'm going to just say that this side, this lobe of this here, this is, right, this lobe here is hatched, you know, it just shaded in here. That guy here is one type of wave function. Let's just say that's a wave function. All right, that's just psi 1. Sorry, psi positive here. This guy here is also a psi positive here by also darkening this in here. And what happens here is that this guy here, these are both the same wave function. So this guy here adds together to give you this guy here, which is going to be the psi positive side and the psi negative side, right? So there's that. So that's what that is. All right, and so that's what we mean by that. All right, and we talked about this before already. All right, and here's, I think, sort of where we ended off last time, more or less. And here's a number of pictures for you. You have a number of these sp3 hybridized orbitals, and they combine together to give you this thing here, which I just drew out for you. You have a number of these things, and you tie them all together by this central crux right here. It will look something that looks like this, right? And each one of these wave functions here, right, each one of these orbitals here that are available for sigma bonding are going to be 109.5 degrees away from each other, right? And that's just because they inscribe the interior of a tetrahedron, right? The tetrahedron, right? And how is that determined? It's literally, if you take, like I said before, like if you take like balloons and you crease a long balloon about 3/4 of the way down here, and you know, sort of twist it up right there, and you tie 4 of these balloons together, 4 of these guys here together, you will make this. Like, that's why. It's just it's a giving the largest lobe of the orbital the most space possible. That's all it is, really, right? A simplified version of this is actually this. Notice down here they drew in the other sign of the wave function, you know, orbital type here, you know, the minus side here. Notice here on the simplified version here, we have no such negative sign that's drawn in. All right, we just put in the positive wave function, and then that's all we did. You know, that's all we did. All right. And yep, and so then what happens here is that now you have these sp3 hybridized orbitals right there, right there, right there, and right there. And then you can add to them your 1s orbital, 1 electron from hydrogen. And when they hook up, these two guys here spin pair, they pair together, and they form a sigma bond. So where do these electrons here come from? All right, I'm going to go back here, and I'm going to lose all this scribbling here. But as I go backwards, and now remember, this is an sp3 hybrid carbon, right? These electrons here come from these guys right there. 4 degenerate sp3 orbitals. These guys here make up the sigma bonds. All right, they make up the sigma bonds there. All right, so each one of these guys here make up each one of these guys here and here to make up your sigma bond. Okay, that's how that goes. All right, that's the simplest of all hybridizations for carbon. sp3 hybridized. It's called saturated because it has the maximum number of hydrogens possible, and that's what we call saturation in organic chemistry. Now consider, if you will, ethylene or ethene, and you'll learn these names very soon, right? Ethylene here is a carbon. Is comprised of a carbon here that has a double bond in it, right? One side of the bond here, right, is called a pi bond. The other side of this bond here is called a sigma bond, right? Each of these bonds here that have a single bond here are also sigma bonds as well. Right, sigma bonds as well. Sigma bonds, all right? You can't have a pi bond without first a sigma bond. The sigma bond is the framework for all of your organic structures, right? You just can't say, I'm going to have 2 pi bonds and no sigma bonds. Nope. You have to have a sigma bond first. That's just how it goes. And then this pi bond here comes afterwards, right? Now, how do you make these, how do you understand these things here? Well, first, I'll tell you, okay, so you have, here's ethylene here, which is a carbon, double bond carbon with 4 hydrogens on it, like you see in the pretty picture right next to you. Why I'm drawing my scribble next to it, beyond me. But you draw this guy here, and you say, okay, this guy here is an sp, this is an, each of these carbons here are sp2 hybrids, sp2, right? How do we know they're sp2 hybrids? Well, remember the cheating way I showed you, the sort of the little shortcut? sp2 is comprised of 1 s and 2 p orbitals. So overall, 3 things. Just to say 3 things. They're orbitals, yeah, that's great. But let's just say 3 things. There are 3 discrete, if we're talking about this carbon right here, there are 3 discrete things around that carbon. That's how we know it is an sp2 hybridized carbon. There are 3 things around that carbon. 3 letters, 3 things, that's how we know. All right? See, not too bad. It's a cheat, but it works. It actually does work. And it gets you to get the knowledge quickly into your head so you can really go back and really figure out what the hell it really means. That doesn't mean that. Really, it just means that you can solve the problem first and then go back and figure it out. Okay. So we say, okay, now here's what we want to do. We take our excited, remember, this is our excited carbon, right? Now we are told, I will ask you politely, please hybridize to the sp2 hybrid carbon. And you say, no problem, sp2, spp, or sp2. That means I can take 2 p orbitals and 1 s orbital, mix them together, okay? I'll take these 2 p orbitals, take the remaining 1s, take the remaining s orbital here, smush them together, add them together, and I'm going to make that guy right there. I have an unhybridized 2p orbital, unhybridized 2p orbital, which is going to stay right where it is, from there to right there. So in every, and this is so important here, in every sp2 hybrid carbon, you have 3 sp2 orbitals that you made and 1 unhybridized 2p orbital. 3 sp2 hybridized orbitals that are degenerate and 1 unhybridized 2p orbital that we also care about if we have a double bond, and 1 of this guy here, which we don't give a shit about. But we do give a shit about this unhybridized p orbital, but not about that one, all right? So we don't care about that, we care about that, all right? And let us sort of now put together this idea of the configuration with the molecular structure and see if we can figure things out here, all right? Before we go on to this pretty picture here, which is pretty easy to see, I want to just point out to you here, right? Remember, if you have an unhybridized system here, the unhybridized things make sigma bonds. The hybridized makes sigma bonds. The unhybridized makes pi bonds if you have them. All right? That's something to know. That means that every one of these guys here, like I said before, there, and if we're just talking about this carbon over here, we're just talking about that little carbon over here. So there, and there. Sorry about the arrow, the stupid tablet. Each one of those guys here are sigma bonds. Whatever's left is the pi bond. That's right there. And that pi bond is made from the 2p orbital, right? The 2p orbital. Now I'm going to keep on like flubbing over my words saying the 2p's, because you have to have a p orbital here and a p orbital here to be p orbital. I'm sorry, I can't see that. I don't know. P orbital there and a p orbital there to be able to make your pi bond. Okay, that's what you need to have. I'm going to erase this one more time and I'm going to draw in the p orbitals for you. Okay, so there's that. All right. So sigma, 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 which we don't care about, but the p orbital here, even though we drew it here, remember the p orbital comes above. You know what? I'm not going to do that. I'm going to draw a better picture on the next slide. Okay. Just what you have to know though is that pi bond, sigma bond, sigma bond, sigma bond. All right. And while we're at it here, sigma bond, sigma bond. Okay. All right. Here is an sp2 hybridized carbon that has 3 equal sp2 hybrid orbitals and 1 unhybridized p orbital. All right. Notice the sp2 orbital here is in, so this guy here, and this guy here are in the same plane, the same triangular plane, right? They are all in the same triangle. All right. So that's something to be wary of. Notice that the unhybridized p orbital that's in the y-axis here is above, right, and below the plane. All right, that's how it has to look. That's how it has to look. All right, and so let's go here, right? So when I sketch out this molecule here, my unhybridized p orbital electrons go above and below the plane, right, of this triangular plane here, and my sp2 hybrid orbitals here, here, and here go around the triangular plane. In the case of ethylene, remember ethylene that we're talking about here, we're talking about a flat molecule that is not in 3 dimensions, it's only flat, sort of, right? And we're talking about, if we're talking about this, if we're talking about this guy right here, this sp2 hybrid orbital here, let's say this orbital here is over there. Let's say this orbital here is over here. And let's say this orbital here is over, let's just say this is your sp3 hybridized orbital. These guys here are in the plane, the same plane, right? The same exact plane. Sorry if that's getting messy there, right? And each of these guys here, your 1s orbital here, here, and your other sp2 hybridized orbital here comes from this other carbon here. This guy here is paired with its electron. This guy here is paired with its electron here. All right? And so I'll show this in a much neater picture on the next slide. All right? But notice, only thing I've shown here so far here, because I don't want to get too messy, is only your sp2 hybridized sigma bonds. Your overlap between your s orbital and your sp2 hybridized orbital, your overlap is your sigma bond. All right? Let's show it on the next slide. All right? Here is your, I'm going to point to it carefully, hopefully anyway. This guy here, it's coming from the carbon. That is your sp2. Here is your s. Here's your 1s orbital from your hydrogen. Here's your sp2 from your carbon. Over there is your sp2 from your carbon. And I'm pointing specifically to the parts that aren't overlapped yet. sp2 carbon. All right, those are just your regular unhybridized orbitals. Now your overlap, where you now have your orbital from your 1s, for example here, like your 1s here, and your sp3 hybridized here, your overlap is where the bond lives. And that pair of electrons right there is your sigma bond. Your overlap is the bond. Your overlap is your sigma bond here. And your overlap here, right, we can be even more specific. It's not just any sigma bond. It is your sp2 to s sigma bond. sp2 to s sigma bond. Will there be different kinds of sigma bonds? Oh, you bet your boots if you're wearing boots. Well, you are. It's probably rainy today, right? So you're probably wearing rain boots. You bet all your rain boots. You can fill up your rain boots with how many different kinds of carbon sigma bonds there are, right? So their sp2 hybridized s is this sigma bond here. Your sp2, right? This guy here is also your sp2 s sigma bond as well. You put that normally in parentheses, normally. Here's what I'm talking about. Here's another sp2 hybridized bond, and here is a sigma bond here. But here, your sigma bond, which is now made of an sp2, sp2. You see how it's different than the other ones? Your other sigma bonds here are made of sp2 to s's. This sigma bond here is made of 2 sp2 hybridized carbons overlapping together to make your sigma bond right there. Notice this. Look at the two little poles here standing upwards here, there and here. These guys here are your pi bond. Look at the distance between your pi bonds. Look at the distance between these two electrons. Notice in your sigma, in your sigma bonds, you have maximum head-on overlap. That means they're just crashed into each other. They're just two electrons that are just pushed together because you have two jutting out atomic orbitals. But with your pi bond, you have at best this little sort of sidelong bonding, and that's side-on or sidelong bonding, however you want to say it. It's effective and strong, but it's not nearly as strong as your sigma bonds. Your sigma bonds are your strongest bonds here. Your pi bond, your overlap between your pi bond here, here's your pi bond here, right? And your pi bond here is made, if we want to put a finer point on it, your pi bond here is made of the 2p to 2p unhybridized orbital of your carbons, your carbon 2p. I want to stick a C over there somewhere. Carbon 2p and your carbon 2p. All right. That pi bond is strong, but not as strong as a sigma bond, because just even look at the cartoon of it. This guy here is further apart than these guys here are further apart than these guys here are. They overlap, but they're just not very effective at it. But they still offer something, and that accounts for something. All right. So if I had to draw this in my scribble, right? If I had to draw like a carbon bond here, and I had to draw the hydrogen here, I'm just going to draw one side of it, okay? I'm not going to draw the other side of it. I'll draw the other side of it. The hell with it. All right. All right, so there's my backbone, my carbon sigma bond backbone. This guy here, this is from your sp3 hybridized orbital. This is from your s orbital that's unhybridized, of course, from your. So you can't have hybridization in your hydrogen, right? Because what the hell are you going to hybridize to? There's no electron. You can't push your electron. It's only in a 1s orbital. It can't jump to another orbital, right? There's no other available orbitals for it to jump to, right? So here you have that, right? And then this guy here comes from this guy here and that circular orbital there from your 1s. Here is your sp2 hybridized orbital here. Here is your 1s orbital here from there. Here's your one electron here from your sp2 hybridized orbital here. Sorry. And here is your other electron here from your other sp2 hybridized orbital here. So this guy here, I should draw a little closer together, is your sigma bond like I showed down there. All right, and then so forth and so on over here for your other sigma bonds here, which I won't draw, okay? But what I want to draw here is now your p unhybridized p orbital. Notice how my unhybridized p orbitals, I'm trying to draw it carefully, are symmetrical. They should be symmetrical, right? There's no reason for them to not be symmetrical because they're unhybridized. They are pure p orbitals. There's nothing that's mixed with them like s orbitals to make them look any different. I just drew my electrons in my p orbitals here, and I'm going to draw just this. I'm going to draw just this. Just that little squiggly little bond, little idea of a pi bond, right? Between that guy here is a pi bond right there. Right? This guy here is a sigma bond right there. All right? I'm just drawing, but notice I'm not drawing a line between the top part of the lobes and the bottom part of the lobes. If I drew two lines on the top here, right, and on the bottom, that would be wrong. That would be notating that there's some other additional bonding event on the other side of that lobe, and that's not correct. It would almost look like a triple bond, even though that triple bond would be incorrect. Because triple bonds are a lot more difficult to draw than this. They have the p orbitals here are in different axes, right? So this p orbital, right? These p orbitals here have to be on the same axes, right? So take this and print this out if you want. Take a screenshot of it. Again, remember the copyright. Don't let me kill and sue you. All right. Notice this though, okay? look at the 2p orbit. Look at the 2p orbit here, right over here. These guys here, ba-bing, ba-bing, have to be in the same Cartesian coordinate, essentially. They both have to be in the y, the z, or the x, whichever the hell you want to say. But they have to be, whatever it is, which it doesn't really matter, but they have to be the same. So these both have to be like, let's just pretend they're in the y. So this guy here is actually from the, this one of the 2p orbitals here are from the 2py. This other guy here is from the 2py. Now, whenever you draw a pi bond, this is putting the coordinate, the axial labels are maybe redundant, but it's science, and you want to make sure that everyone's on the same page. All right. So that's not a bad thing to be, all right? So you can be a little redundant and you're still fine. So there's your y, there's your py, 2py, here's your 2py. They have to be in the same coordinate because they have to have overlap. If one was 2px and one was 2py, they would be at odds with each other. They would be orthogonal. They would not, orthogonal means that they don't have any association with each other, and so they wouldn't overlap. All right, so you have to have the overlap of your p orbitals there, okay? So here's my crazy scrawlings. So there's that, all right? When I really look at it, it looks like I have a real problem. And I sort of, well, I have a problem. Who doesn't have a problem, right? If my only problem is organic chemistry, I'm doing pretty okay, right? So that's not that bad, all right? And that's not my only problem. I don't want to get into it, but you just don't even want to go there. Anyway, I'm just going to continue. All right. Blah, 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 side by side, orbital overlap, yada, yada, yada. We talked about that already. So that's, and here's a pretty picture of what I drew. What is not here, though, is that, just sketch in your p orbital electrons to show you that you do indeed have those here, right? So here, again, is your book's idea of being clear about it, okay? So if you have a double bond here, it consists of one sigma bond and one pi bond. sp2 hybridized carbon, we talked about that already. What's good to know about this is that, you know how on your tetrahedral carbon and you have four things around it, you have one thing in the plane of the paper, two things in the plane of the paper or the screen, one thing coming out at you, which you have to have, and then one thing sort of going away. You have to have this little tripod thing going. Each one of these guys here is like 109.5, all right, degrees. But if you were to take these two guys here and take these two guys here together, and you just tape them together, right? When you do that, then you force everything into the same plane. And when you do that, what happens here is that you get roughly around that sp2 hybridized carbon. This is sp3. But if you have this sp2 hybridized carbon here, you end up making bond angles that are roughly 120 degrees away from each other. They're not identical. They're not the same. So between this carbon, and this carbon hydrogen, this is roughly 120 degrees. Between these carbon hydrogen bonds here and here, these are roughly 120 degrees, but these are different in terms of numbers from here to here. Like they are not all the same. That just does not happen that way. But you know what? For this course, for undergraduate organic chemistry, which is it's not physical organic, I am going to be happy with you knowing for an sp2 hybridized carbon, I want you to know that you have to have, 120 degree bond angles. That's what I want you to take home from this, okay? Acetylene, which is one of our last examples of this ridiculousness here. Now, instead of having, ethylene here, acetylene or ethine or acetylene here is a carbon here which has two things around it. So if there's two things around it, that must mean that it must be comprised of an s orbital. The hybrid orbitals must be comprised of an s orbital and a p orbital, 1 and 1. So they are an sp hybridized each one of these carbons here are sp hybridized. Can we confirm this? Sure. It's sp hybridized because I take one of my p orbitals here, one of my s orbitals here, I combine them, and I hybridize to make two degenerate sp orbitals. That means I have two things around the carbon. Two things, which is thing 1 and thing 2, if we're talking about this carbon over here. Okay. So there's that. So that means that if that is the case, that means that this must be, I must have two sigma, I must have two sigma bonds there. And do I have that? Oh, show. I have that guy there, which is a sigma bond, and I have one of these guys here, which are also a sigma bond. All right. The rest of this BS over here, there and there, are both pi bonds. Are they different? Are they the same pi bond or different pi bonds? They are two different pi bonds. All right. And those two pi bonds here come from, remember, we're talking about just one. This is just this guy here. This guy here is just a single, it's just one carbon in the entire molecule. And for the purposes of argument, it's like this carbon. All right. This is the one carbon that we're talking about. This molecule here has two orbital diagrams. One, and they both are identical. So this guy here that we're talking about is for this carbon over here. Each one of these pi bonds here has one of those p electrons there and one from there. So one of these pi bonds here, that's one of those electrons, and here is the other electron. Now, since we talked about coordinates the last slide, let's talk about coordinates here. These guys here cannot be in the same, these guys can't be, you know how in all the p orbitals you have to have coordinates? And in these unhybridized p orbitals here, they also have to have coordinates. But they just can't be the same ones. So let's just arbitrarily say this guy here is px, this guy here is in py, right? Because that's how the hybrid orbitals in acetylene look like. All right, let's see about the next page here. All right, here's what it looks like. All right, and I'm not going to draw out this guy here with my pen because it's too sloppy for this medium here. But I will ask, for your exam, I will ask you to draw out some hybridization diagram of some carbon that is, carbon or nitrogen actually, that is going to be an sp2 or sp3 hybrid orbital, that has hybrid orbitals in it. So please practice that. All right, so let's just go into this. All right, this guy here is your sigma bond from your what from your sp hybridized carbon to your 1s, sp hybridized carbon. Let's do it. Let's put sp carbon, 1s hydrogen over here. All right, that's where the sigma bond comes from. This sigma bond over here comes from your sp hybrid, from two of your sp hybridized carbons, your sp carbon and your sp carbon. And here are both of your sp. So each carbon in this acetylene molecule is an sp hybridized carbon. So that's why you have two carbons here, that the central backbone of this molecule here is a sigma bond from these two sp hybridized carbons. And that's what that is, right? And so that's what that looks like. Okay. What else? Okay. And this other side is this other side here is the same as this side over here. Okay. So there's our sigma bond framework. Each of these sigma bonds here, right? One side of them, if we're talking about this carbon here, and I'm going to flip back now to the other slide. Each of these sigma sp hybridized carbon electrons comes from, remember, there and there. Each one of these guys here, remember, and I think we said what, 2px and 2py, right, come from these unhybridized p orbitals, and we will now label those. Okay, notice here is one pi bond here, and notice that this pi bond right here is made up of this a p orbital that they are in the same plane. So let's just say that this pi bond right here is comprised of 2py, let's just say 2px and 2px hybrid orbitals, right, 2px from, you know what? Don't copy that down. Let me erase. Let me say this pi bond here, because I want to keep our nomenclature the same. Our pi bond here, if we're talking about this pi bond right there, right, comes from this 2px, and that comes from this carbon, right? This comes from this carbon over here. And this guy here comes from the other 2px that comes from the other subscripted carbon. All right? So these are both 2px unhybridized 2px orbitals. These orbitals here from these pi bond, from these p orbitals here, are in the same x coordinate. You know, x coordinate. That's all we're talking about. Let's just say that the thing that's pointing up here, and I'm just drawing it out, just so you can. That's uncharacteristically neat for me right now. I have no idea why I accidentally made that so nice looking. All right, so there's your x, and this is the colored part that we care about that's overlapping. All right, and so now, that's one half of our pi system. Our other pi system here is exactly the same, except it's not in the same coordinate. This guy here, let's going to say, is going to be in p. We would say what, py. This pi bond here, this pi x bond here, is different from this pi y bond, because now this is now 2py from the carbon. This guy here is now 2py from the other carbon, because these guys here are in the y coordinate. And again, there's that, and then here is here's now our y coordinate p orbital, and that's why that is. All right. So 2px, this is from the 2px. This is from the so this pi x is from the 2px unhybridized p orbitals. This other one here is the pi y from the 2 pi y orbitals from each of the carbons. Okay. And then the sigma bond framework is the sigma bond framework which we already talked about. All right. So remember this, remember 2px, all right, I'm going to flip back to the other slide, right, 2px, sorry, keep on saying x, I draw y, all right, and here's your 2px, here's your 2py, making up each of those pi bonds here. And as you can see, look at how simplistic now this bond line notation looks like almost, right? Because it doesn't show you anything about 3 dimensions or where those pi bonds are, but you know, we need to know details when we need to know them. We don't need to know all the details all the time. It's good, you know, it gets cumbersome sometimes to just get all the details all at once. So let's just use what we need. So to draw these things here, I will ask you to draw an sp2, I'm sorry, an sp, sp2, and an sp3 hybridized carbon or nitrogen. Nitrogen is very similar to carbon, okay? Just with a different number of electrons, so just be very careful there. All right, difference in strengths and lengths from before, or from the double bond, triple bond, and single bond here. You have a carbon-carbon single bond length. It's 1.54 angstroms. Double bond is 1.34, 1.2 angstroms. Here is your triple bond here. Each of them have, as you add more bond energies in between those two carbons here, as you add multiple bonds to them, the distance between the carbon-carbon bonds becomes lesser and lesser. All right, as shown by these bond lengths right here. But look at the bond energies. They go way up from there, from single to double, then from double to triple. All right, does that make sense? Sure it does, right? Let's imagine that this is just a rope or elastic band between this carbon and this carbon here. You only have one rope or one rubber band. But now between these two carbons here, now you have two ropes. Or this is probably rubber bands, probably a little bit better. Rubber band, you know, you have two rubber bands here, which are now pulling the two carbons closer and closer together here. That you have one bond, here you have one bond, here you have two. Two is stronger than one. That's just that's the level of detail that we're looking at this point here. 3 rubber bands versus 1 rubber band, of course, is going to be a lot stronger in terms of bond energy. Not quite triple, but because why? Why do you imagine? Well, I won't wait for your answer because it's just a one-sided conversation at this point. But it's like most of my conversations with everybody. mostly one-sided. I'm just talking and waiting to talk because I'm a blabbermouth, right? So this guy here, 820 is not 3 times 368. It's not that at all. But why is this lesser than 368? Well, because, and I'm going to flip back a few slides. Remember this? Where the hell is it? Did I lose? Did I go by? I went by it. I must have went by it. Yes, here it is. Sigma bonds provide a maximum head-on thing, but your pi bond here provides a side-by-side. It's not plain old pi bonds by them, all by their lonesome is not. They're not as strong because they don't have efficient overlap. The most efficient overlap is two head-on electrons from hybridized orbitals. Right, that's from the sigma bond. Whenever you throw on some pi bond energy here, that's great, but it is absolutely not the strength of a sigma bond. So you can add on a lot of pi bond energy, which is what you're doing from here to here and from here to here, but you're just not adding sigma bond energy. And when you do that, yeah, it gets closer together, the two carbons. Yes, it gets stronger, sure, but it does not get sigma bond strong. It gets pi bond strong, but not sigma bond strong. So that's one thing you have to know, all right? And make sure you understand that. Pi bond energy is all great. It's a real bond, honest to goodness real bond, but it's not the same as full-on front to front bonding, period, okay? Molecular geometry here, and here's something, and do you have to know any of this crap over here? Not really. I'd like you to know this stuff here, right? If you have sp hybridized carbon here, chances are your bond is going to be linear because there's only two things attached to a central atom here. If you have an sp2 hybridized carbon here, chances are if you have 3 atoms attached to that carbon here, it's going to be trigonal planar, and roughly the angles will be roughly tilde, right? Tilde Swinton. Roughly it'll be 120 degrees, roughly speaking here. In the same way as like if you have 2 things attached to a central atom here, this would be 180 degrees roughly. But that's if you have 3 atoms attached. If you have 2 atoms attached, you will have tired here. If you have 2 atoms attached and a lone pair, then the molecule itself will be bent because why? Because this electron here is taking up a bunch of room and it is repelling the other 2 things attached to it. It's still pushing the other 2 things away like you have here when it's triply attached. But if you only have a double attachment, that electron pair is still pushing things away from itself because, remember, this electron pair is unbound now, and it is very close to other electron pairs which are bound up. Still, though, they're electrons. They have minus charges. They don't want to be next to each other. It's negative. It's a negative. They're just negative charges, and like charges repel, just like in magnets, essentially, right? All right. So tetrahedral, 109.5. If you have 4 things attached to a carbon or a nitrogen that is sp3 hybridized, chances are it'll be tetrahedral. If you have 3 things attached to it, you will have that 1 lone pair up there here, and that will push down on the other 3 substituents or other 3 things attached to that central atom, and that will give you a trigonal pyramid. So the term here is trigonal pyramidal, a trigonal pyramid. Let's say you pull off 2 things around that carbon here or nitrogen. You'll have 2 lone pair there and there. That will end up giving you a bent structure right there. The most famous bent structure that you know of is the most famous sp3 hybridized element probably that you know of is water. Oxygen there has 2 bound electron pairs and 2 unbound electron pairs. Those 2 bound electron pairs are rabbit ears, and those are pushing down on those other 2 hydrogens, making it an overall bent molecule. All right, cool. If you want to figure out, if you want to do the steric number thing, I know some books have the steric number thing, do that, but don't get all hung up on it. Oh, by the way, this thing is called VSEPR theory, valence shell electron pair repulsion. That means if you have electrons around your central atom, which we do all the time here, unbound electron pairs take up more space than bound electron pairs, and they will affect the geometry of these things. So VSEPR theory is a thing that gives us, through electron pair repulsion, because no negative thing wants to be close to one another, it gives us these shapes that we are familiar with, right? In the tetrahedral here, you have four electron pairs here, which are all sort of bound up, and that's all well and good, but they still don't want, they want to be as far apart as possible. And believe it or not, if you have four things tethered to a central thing, the four positions around it will inscribe a tetrahedron, right? And as you stop pulling atoms off of those electrons here, you'll end up getting a trigonal pyramid or a bent molecule. That's what that means, okay? So here is, for an sp3 hybridized atom here are, the three main geometries here. If you have four atoms, you have a tetrahedron. If you have three atoms here, you have a trigonal pyramid here, because this lone pair here pushes down on all these other electron pairs of the other bound atoms here. And if you have two lone pairs there and there, then again, that will still give you the maximum. It'll push away in a maximal fashion everything else that's around that oxygen, all right, to give you the most space possible. And notice the angles here to here to here. As you decrease the number of things around the carbon or the nitrogen, you also, as you decrease the number of things around that central carbon or nitrogen, you decrease the angles between the existing remaining atoms, 109 to 107 to 105. How can you explain this? No problem. Bound, like I said before, unbound electron pairs take up more space than bound electron pairs. As you are having all this electron density that is now unbound, it is now free to be a very, very negative charge. It's allowed to be much more negative. And if this is a discrete negative charge here, and this is a discrete negative charge here, or more negative, it does really not want to be it does not want to be very close to each other. So these guys here will pull each other, will just jut away from each other. It's like, I am out of here. So as this angle here is increasing here, going up, this angle down here is going down, just based on basic geometry. This guy here is they don't want to be far apart, so they're pulling away from each other. So this guy here will be further away. All right, and I will show you more of that on more of that when I see you next. Okay. All right, and here's another fun little table if you want to know this or not, but you don't necessarily have to. Okay. But I mean, I won't want you to know a table to memorize it. I want you to be able to derive all of your concepts. Okay. Same thing here. And here's boron trifluoride. Three things around a center. If you have three things around a central atom here, the maximum space is going to be 120. Again, that's just basic geometry. It inscribes a circle. If you inscribe a circle and you cut it in half three ways, you get 120 degrees between the atoms. All right. And again, you still have sp2 hybridized species here, but you have a lone pair here. Okay, so the hybridization of this is an sp2, right? sp2 right here. But this guy here is not going to be a trigonal pyramidal. It'll be a bent molecule. Why? Because whenever we look for molecular geometry, all we do is we count not the electron pairs. That helps us to know the angles and stuff in hybridization. But in terms of what to call it, is it going to be tetrahedral or trigonal was it the trigonal planar or a tetrahedral or a linear? We just look at the atoms around that central atom. All right, and so if we see that this carbon here, the CH2 to nitrogen to C3 here, forms a bent shape, right? So even though sp2 hybridized isn't really listed in the common things of having a bent shape. If you have a lone pair on an sp2 hybridized atom like a carbon or nitrogen, you indeed can have a bent molecular geometry. A bent molecular geometry. All right, and here's another cute little table if you want to look at it too. Again, please don't memorize. Please derive. Please derive. Derivation is the only way you're really gonna get a much better grasp on this thing. All right, and here's your again another table too. Your book does it, I think, and even the other previous book also does the same exact thing. Now, cis-trans isomerism. All right. Stereochemistry is a term that we will talk about at great nauseous length soon, but not right now. Just suffice it to say that stereochemistry is the position of atoms around a molecule in space. This R group here is shorthand for any alkyl group. And by alkyl, I mean CH2, CH3, CH, that kind of thing here. All right? But notice you have a carbon-carbon double bond here is the same as this. So this guy over here is identical to this guy over here, even though the R is pointing downwards. And this guy here is R is pointing upwards. It just means that I just took this guy here and I just flipped it around, the entire molecule as a model, to give you this guy right over here, right? So if I take this guy here where I have a methyl on this side here and an isopropyl on this side here, if I flip it around, if I just flip it, where now the isopropyl here is on top and the methyl here is on the bottom, all right? All I did was I just flipped it from there to there. That's all I did was I just flip 180 degrees. That's all I did, okay, to give you that species over there, all right? So the difference is that now, let me just make sure, all right, is now when that does happen, that's all well and good, but let's say the substituents are on opposite sides of the double bond, all right? Hey, look at this, all right, carbon, carbon, me is methyl, right? You know what? Let me draw a better picture. Let me draw a better. So carbon, carbon, hydrogen, hydrogen, chlorine, chlorine. All right. These two chlorines here are said to be on the same side, are on the same carbon here. So I really can't are on the same carbon. So I really can't have any type of differing of this chlorine to this chlorine in space. The only way I can make these two chlorines here different in space is if I put them on the opposite ends of this double bond. And that's what we're showing here. If I have a double bond, right, in the smack dab in the center of this molecule here, right, and I have two different things other than hydrogen, and this methyl here is on this side here, and when I cross over the tracks, I jump over the tracks here. When I jump over the tracks here, this guy here is on this side, and as I jump over the tracks, I see, and as I go further, northward here, I see this guy over here is on opposite sides of the tracks, on the other carbon. All right, this guy here is said to have a trans relationship. These two methyls are trans to each other. Trans is a stereochemical descriptor. That means that this guy here describes these two methyls relative to each other. This guy here is called cis, and cis arises when you have two of the same substituent, two of the same thing, on the same side of the railroad tracks. Right? Same side of the railroad tracks, cis. Different side of the railroad tracks, trans. These are stereochemical descriptors, and that's all that is too. Why do we care about that? Because if we have a carbon-carbon double bond, we cannot flip around. We can't break a double bond here because it doesn't have free rotation, because that pi bond here is restricting the rotation of that carbon-carbon double bond. Remember, here's your carbon-carbon single bond, which has free rotation. But if you have a carbon-carbon double bond, remember there's your sigma bond right there, and here is your pi bond. And that pi bond here just sort of like locks the rotation of each of these two carbons together. If you play with your model set, you'll see exactly what I mean. Make a double bonded species with your model set versus making a single bonded model, a single bonded set, and you'll see that with a single bond you can propeller, one side of the molecule versus the other side. Okay, but if you have a carbon-carbon double bond, that rotation is restricted, and if you have a restricted rotation here, that means they are different molecules, and that's why they have different stereochemical descriptors. Okay, so I think that is all for this chapter. Hello folks. Okay, let's talk about chapter 2, which is the families of carbon compounds, functional groups, intermolecular forces, and infrared spectroscopy. We won't cover the entire chapter in this lecture, but we'll just cover the beginning parts of it, and then we'll finish it up when I see you next. Okay, so let us go here. All right, so major functional groups, and we'll talk about what a functional group is and why it's important, the correlation between properties of functional groups and their intermolecular forces, what makes them so special, and infrared spectroscopy, which tells you sort of the identity of some functionality or some functional groups based on how strongly these functional groups, which are small collections of small subcollections of atoms bound together, and how they can imbue certain molecules with very specific properties, and also how you can pick those out using infrared spectroscopy. All right, so hydrocarbons is what we're talking about for the past few days here. Our carbons contain only carbon and hydrogen, and for the most part, the things that we talk about mostly are alkanes, right? But alkanes are sort of weird, and they're not very reactive because they have full saturation. That means you have, for every carbon, you have the maximum amount of hydrogen you can have for that carbon. For example, here in pentane, you can have you have 1, 2, 3, 4, 5 carbons there. On each of those 5 carbons, if you're talking about the end carbons, each of those carbons there have 3 hydrogens on them. If you're talking about the interior carbons, they have 2 hydrogens on them. In cyclohexane, you have each carbon has a maximum of 2 hydrogens that it could possibly support because of its saturation level. All right, they are called alkanes, and notice that the prefix like pentane or cyclohex, as in cyclohexane, describes sort of the overall number of carbons in them as a noun, or what their rough arrangement is. But the point here is that the suffix ane refers to alkanes. All right, alkenes, which we've seen before, is anything with a double bond, like propene or cyclohexene. And notice that the first part, the prefix, does not change at all. Pent and cyclohex to well, in this case here it's propene. So prop would be the same thing if it was a completely saturated system. So if it was propane, it would be still prop. But here you have propene for propene. That means that you have a propyl group, and in the propyl group somewhere you have a double bond, hence the ene. In the cyclohexene, you have a cyclohex sort of parent here, all right, as in the previous slide, cyclohexane, cyclohexene. And it just means that in your cyclohexyl system, you have a double bond in there somewhere, and we have yet to determine where that is. And for alkynes, finally, you have ethyne, pentyne, or 2-pentyne. For our examples, eth and pent just means, the ethyl just means there's 2 carbons. The pent just means that there's 5 carbons associated with it. And if it's the simplest triple bond, like 2 carbons for ethyne, you don't need to tell the reader or the scientist where that triple bond is, because it can only be one place in ethyne. But next door there on the right, 1-pentyne and 2-pentyne, notice that in the 2 examples that we've chosen there, we've chosen that the triple bond species is actually at the beginning part of the chain, right? And that is why it's called 1-pentyne, because it begins on the first carbon. You would start numbering the carbon from the closest edge of the last carbon through the triple bond. That's how you number pentene, alkenes and alkynes. So on the top one here, you have 1-pentyne, because your first carbon that has the double bond is on the 1 position. But on the second example, 2-pentyne, notice that the molecule there begins from the right and is labeled from right to left. And that is why, because the closest carbon that has the beginning, the lowest number carbon that has the beginning alkyne on it is carbon number 2. It's the second carbon in. So we begin from the right. 1, 2, 3, 4, 5. The triple bond begins at carbon 2. That's why it's a 2-pentyne. So the whole rule here for nomenclature, for naming systems here, is give your functional group here, in this case here, the lowest possible numbering if you want to tell somebody where the functional group is. And that's a general rule. Lots of exceptions. We'll see. Aromatic compounds. It contains a special type of a ring, the most common example of which is called a benzene ring, which no doubt you've heard of benzene before. Why is it called aromatic? Well, because of what you think it is. Aromatic smells. Things, they're sort of smelly. They have a certain odor associated with them too. But there's another thing to aromaticity that we have to talk about, which would be a lot later in the course. It's not. It's a pretty big topic, and we can't squeeze it in right now. But if it's an aromatic compound, if the main part of the molecule is a benzene. So there on the bottom left is benzene. If you have one methyl group here on it, it's called a toluene. Or for example, if you have a carboxylic acid group on it, it is a benzoic acid. But all those guys here are roots of the benzene functionality. Alkanes. The primary source of the alkanes are natural gas and petroleum. The smaller alkanes, methane through butane, are gases mostly. Methane is the principal component of natural gas. And higher molecular weight alkanes are obtained largely through refining petroleum, like oil petroleum, that kind of thing there. And there's our favorite methane molecule down there in the sp3 hybridized carbon state. There is the bond stick model, and there is a likely source of lots of methane there on the lower right. Alkenes are they are reactive species here. They're very simple. They're very important things. Alkenes are the starting material for so many things, including ethanol, which is a popular beverage that the young kids like to drink to have jollity in their life. Ethylene oxide, ethanol, which ethanol is the principal component of yogurt that gives it its sour taste, for example. And also, it's the initial components of the polymer called polyethylene, right? So ethene has lots of starting materials, for lots of important processes. So, we can barely touch on them, but we will go through many of those things as we go on in this course. Propene is the most important. Propene, which is it's the triple bond version of the double bond. I'm sorry, not the 3 carbon version of the ethene species here. It's an important starting material for acetone, cumene, and polypropylene. So propene, try and figure it out. Try and figure out how to draw it out. It is like ethene, except it has 3 carbons on it, right? And still only 1 double bond. So why don't you try drawing up propene there at the top of the slide there, right? So examples of naturally occurring alkenes, and there is just a ton of them out there too. These are just 2 random ones, which for some reason I don't know why I just did. I just grabbed these guys here. Beta pinene, which is a component of turpentine, and this weird cyclic species here is an aphid alarm pheromone on the right side over there again. But these are just 2 random examples of double bond species here. Beta pinene here doesn't seem to have it seems to be a no double bond in that guy. So let me get back to you on that. There seems to be a typo in this slide. Let me get back to you on that one, okay? And alkynes over here. The simplest alkyne is ethine, also called acetylene. You may have heard of acetylene before from oxyacetylene, as in oxyacetylene torches, that kind of thing. Carbon-carbon triple bond. Both carbons are sp hybridized, so there's that. And naturally occurring alkynes are capillin, which is an antifungal agent, or dactylin, which is an inhibitor of a phenobarbital metabolism. So again, there's lots of triple bonded species that are naturally occurring. Okay. Benzene here, it's weird. Here's a weird thing. All right. So benzene. So no doubt we've seen a few days ago that double-headed arrow there, right? That arrow is a resonance arrow that you've come to notice. And if you have benzene on like the left side, you see how it's drawn with those alternating double single double bonds there, right? And if you look to the right of that arrow, you'll see that those same bonds are there, but now they've shifted one carbon over. And that's meant to say that the left side of that drawing is also the right side of that arrow there, and so it's one and the same. So because they have resonance there. And sometimes you can draw a really very what do we call it? A resonance hybrid, or sort of an abbreviation of benzene, with the furthest structure over there to your right, which is the cyclo. It looks like a cyclohexane with a circle in the middle of it, but that circle is meant to show sort of like electron motion or electron movement in that pi system, in that alternating pi system. And that's an effective way to draw benzene, and it's correct. Is it completely like Lewis dot structure correct? Of course not. It's ridiculous, but it's an abbreviation that is an acceptable abbreviation that we're all cool with. So feel free to draw benzene in that way, as long as it doesn't affect your mechanism. If it affects your mechanism, then please draw the benzene with the double bonds as shown there on the leftish side. All right. All the carbon-carbon bonds in benzene are the same length, which should sound weird to you. Roughly 1.3 angstroms. Compare the single carbon-carbon single bond here is 1.54 angstroms, and the carbon-carbon double is 1.34 angstroms. But notice you have alternating. If you look at benzene on the top two left and center structures there, you'll see that you have a double single. So why isn't the double bond 1.34 angstroms and the single 1.54? Why are they all 1.39? That must mean that there is some movement between the double and the single bonds in some sort of a pattern that will average out all of the bond lengths to be equivalent. All right, and that is what we indeed do see, because benzene is in resonance, which is why we could draw that ridiculous structure on your right side, because that circle there represents the fact that all those pi bonds are running around that inside of the ring, and allowing each of those carbon-carbon bonds to sort of average out to a 1.39 average angstrom length. All right, and benzene here is sort of extra stabilized due to the resonance, right? And resonance here is a stabilizing factor. That's why it happens spontaneously. It lowers the overall energy of a system, even though it is compressing the bonds a little bit. It overall is lowering the energy of the pi system, right? If you didn't have a pi system there wouldn't be anything to lower. But since you have a pi system, overall it prefers to be resonating, which is something that which is a topic that we'll have to keep on using for a while. Resonance is, you'll see how we don't believe in resonance in a while, but for right now we do. All right, and it is aromatic, and we will talk about that real definition of aromaticity later on. Okay, here's the 3D structure of benzene. Now, if we say to each other, well, all the single bonds around carbon bonds in benzene, one set has to be sigma, and that's what you see there in the red. The red are all your sigma bonds there, but above or below the plane of the sigma bond framework is your pi system. So there is your lobes upper or on the upper part or the lower part of that too. And so what I don't want you to get confused by is that there is a line. The publisher drew these bottom lines dotted lines there, and that is a mistake on their part. That is incorrect. Only look at the top dotted lines for the pi system. Why is the pi system in that dotted line over those p orbitals? Because how can we rationalize putting p orbitals on each carbon of the benzene ring? Here's why, right? If we look at benzene ring, each of those carbons are sp2 hybridized. Every sp2 hybridized carbon, remember from last chapter, is every pi bond, every pi bond comes from an unhybridized p orbital. And on every carbon of benzene, you have an unhybridized p orbital, which is right there. Those are the unhybridized p orbitals which are making up the aromatic framework of that system, right? So you only have resonance, right? As you remember from resonance, you only have resonance if you have, alternating p orbitals that form pi bonds. So there are your p orbitals, right? Unhybridized p orbitals that can now engage in resonance, and that's what we have there now. The electron density can be either above or below the ring. Not electrons are above and below the ring. They are either above or below, but they are not there at the same time. They're not there at the same time, right? So they can't occupy that. There's only one, in order to have bond pairing, you can't, you have to have, either above or below, okay? Benzene, if you look for the bullet points below, is a planar structure. All carbons are sp2 hybridized, and all these pi electrons are delocalized. Delocalized is a fancy schmancy, sciencey word for not local, for not stationary. Delocalized just means moving around. If you're just saying, like most of the time I'm lecturing, I am standing behind the podium, right, and I'm local to that podium. But if I am pacing the floor back and forth between the podium and the other side of the lecture hall, I am delocalized, right? So if I'm local to something, I am standing right next to it. If I am delocalized, I am wandering around in a certain, maybe in a certain area, but I'm not staying still. All right, that's what delocalized means. All right. So again, here's something that we want to make sure that we remember here is polar covalent bonds here, right? We want to make sure that we know this. All right. Polar covalent bonds here are things that are that have equivalent. If we're talking about the 2p orbitals, things that have covalent sharing of electrons here, but they are differing in electronegativity. Like for example, if you had a carbon bond there and you had a fluorine, if you had a carbon-fluorine bond there, the differences of electronegativity between fluorine and carbon here are, it's going to be 1.5, right? And that 1.5, of course, is going to be on the Pauling scale. Okay. And so, hey, okay, let me just see if I can get this animation to work. If I can, I don't know if I can. I'll show this animation to you when I see you next time too. But yes, that's Keanu Reeves, and he'll be animated when I show this to you. But so here's just a picture of the polar covalent bonds, and I'll show you the little animation that's associated with it. All right, dipole moments, polar and nonpolar molecules. This is like a little rehash of your Gen Chem days. Hopefully it wasn't too traumatic, but there's that. Dipole moments are expressed in debye, where 1 debye is equal to 3.336 times 10 to the minus 30 coulomb meters. That's in SI units. The definition of a dipole is a dipole moment is a measurement of the separation of two oppositely charged charges. Dipole moments are a vector quantity, right? That means that they have a directionality associated with them. That's what a vector is, not a scalar. A scalar is a number. A vector, sorry about the geometry lesson here, folks, but that's just what it is, right? A vector quantity has magnitude and direction, right? The magnitude is equal to the charge multiplied by the distance between the charges, and that direction is from negative to positive, right? That's what it is, all right? And so again, this is, I'm not going to hold you to any calculation of dipole moment, all right? So don't worry about that, all right? So here are the molecules containing polar bonds and are not necessarily polar as a whole. For example, here are boron trifluoride has a 0 dipole moment, We draw the dipole going from the boron here to the fluorine. So go from your most positive, right, to your most electronegative according to the periodic table, and that's where you draw your arrow. Some people draw the arrow. Some people draw the arrow like you know, on the bond itself. I don't do that. I draw like a little arrow with a cross sign, you know, on the side of the more electropositive element, and then I draw that arrow pointing towards the more electronegative thing. So notice if you have the boron in the center and then your fluorine's pulling on every side of it, with a distance of 120 degrees, it's pulling equivalently on three sides of it. And then when you do that, you pretty much cancel everything else out. Similarly, with the tetrahedral nature of carbon tetrachloride there on the right and on the blue, you see that that each chlorine here is pulling equivalently on that carbon in the same direction, in the same magnitude, right? In the same direction relative to each carbon chlorine, right? And in the same magnitude. And since that happens, you have a zero net dipole moment. All right, I will ask you to draw out a dipole moment of certain molecules because this is a sort of a fundamental thing. Again, this probably is a review from your Gen Chem days. Okay, dipole moment of some common compounds here. Right, here's just a random list. Look at the bottom right. So methane CH4 and CCl4. Notice zero dipole moment. Notice some of the random dipoles there of the carboxylic acids and the ammonias over there too. And those are all good to know. Look at the dipole moment of water to behold that. But look over there in the yellow and the red. Right? Look at the yellow. The yellow for sodium chloride, look at the dipole moment. It's crazy. That's 9. It's 9 debis. That's crazy, isn't it? Does it make sense that it is? Sure it does. Why? Because dipole moment, you don't have to have the dipole moment. Doesn't have to be from a covalently bound molecule. It can be from an ionic compound. And if it comes from an ionic compound, that means inherently the electronegativities are vastly different. They're from opposite ends of the periodic table. And if you have that, then you have sort of a built-in automatic huge dipole, right? Sodium is very positive. Chlorine is very negative. You can't get much more, you can't get can't get much bigger in difference in terms of dipole than that. You can essentially, but it's pretty dang big. All right, so for ionic compounds overall, they're gonna be pretty high in terms of dipole moment. But now look at all this stuff. Look at bromomethane, chloromethane, bromomethane, and iodomethane. 1.87, 1.79, 1.64 in the pink or whatever the hell that color is. Notice the dipole moment goes down as you go down the periodic table from top to bottom. 1.87, 179, 164. Why do you think that is? Why do you think that is? Pause for an infinite amount of time and ponder why that is. I'll wait. All right, are you unpaused? Are you unpaused now? Come on, what the hell? Unpause. I want to talk. You can't silence me. You will not silence me. I shan't be silenced. All right, I'll give you okay, look. Going from 1.87 to 179 to 164, it goes down. The dipole moment goes down as you go down a group, right? Why? Because the electronegativity goes down. As you go up the group towards fluorine, it gets more electronegative. That's why chlorine, the chloromethane, has a bigger dipole than the iodomethane, right? The CH3I is lesser than the CH3Cl because as you go from iodine to chlorine, you're getting closer to the fluorine, which is the most electronegative element on the periodic table. As your halides get more electronegative, then you end up getting a larger dipole within a given series. And the given series here is the methyl group, the methyl series. Now notice, look at this. Look at CH3Cl 1.87. Go just past that pink box to CH3. 1.87 to 1.02. So a much lesser dipole than the so chloroform CHCl3 is a much lower dipole than chloromethane 1.87. Why do you think that is? That is because now you have, instead of just one chlorine pulling in one direction, Now you have 3 chlorines pulling in sort of opposing directions a little bit. It's still giving some dipole, but they're almost canceling each other out. All you need is one more chlorine to cancel the entire thing out, to make it carbon tetrachloride, which is right next door to it essentially, and give it a 0 dipole. Those 3 chlorines there are sort of pulling, all sort of like not pulling in the same direction, but all pulling in a similar direction, but not agreeing with each other. So it is decreasing the overall dipole of the system. And when I come in next time, I'll show you what that looks like. Dipole moments are not just bound to just simple straightforward small molecules. Here you can have dipole moments in alkenes, for example. Look at the carbon-carbon double bond on cis-1,2-dichloroethene there on your left. Your resultant dipole is 1.9 debis, right? And that is because the carbon-chlorine bonds are locked on the same side in the cis orientation, versus the trans orientation on the other side. They are now sort of equal but opposite sides. It's almost like a mirror, not a mirror image, but it's very close to being very symmetrical. And like the symmetry of that molecule is right in the very center of that carbon-carbon double bond. And if you can imagine, the chlorines are pulling in equal but opposite directions from that center of the carbon-carbon double bond, as opposed to the cis-1,2-dichloroethane on your left, which both carbon-chlorine bonds are pulling in the same direction, giving you that giant red resultant dipole moment. Right? That resultant dipole moment is sort of like a visual average, a really roughy, a rough type of like visual average between the two, between the multiple blue arrows, right? All right, functional groups here. Here's where we start talking about like what these things look like and how should we address each of these things too. So functional groups are common and specific arrangements of atoms that impart predictable reactivity and properties to a molecule. Now I'll just read this to you here in the bottom. Organic compounds are thought of as consisting of a relative unreactive backbone, like a carbon, CH2, CH3, CH2 type of a backbone. For example, the chain of sp3 hybridized carbons, and one or several functional groups. The functional group is an atom or a group of atoms that has similar chemical properties whenever it occurs in different compounds. It defines the characteristic physical and chemical properties of families in organic compounds. I am not going to ask you the definition of a functional group. I just want you to see the actual text there. All functional groups are just things that more or less aren't sp3 hybridized carbon crap. Like, for example, these are not functional groups. I don't care who says it. Look, so here's your table. Alkane, methane. Alkyl group is a methyl. Abbreviation is Me. Bond line is a single line. And there's your model set there. These guys here aren't really reactive. I mean, they are reactive under the right conditions, but they are very, very, very unreactive. Like, you can't just throw an acid or base and things happen. You have to have some other thing that you do to them so they become more reactive, okay? So these are not functional groups. Functional groups react chemically with something under reasonable conditions, and reasonable is something that we'll sort of have to define along the way, individually for every person in every situation. So, and we will argue in a friendly way about what does it mean to be reactive to something or not, or why will this react and why won't this react. That's the whole part of organic chemistry. These guys here are so unimportant. In fact, we sort of designate these things by using the letter R. So let's say you have a gigantic molecule that has like a bunch of CH3, CH2, 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 CH, CH3, CH2, CH2, CH3. I need a drink after that. Hold on. This is only coffee, by the way. Normally I drink alcohol, but this is, trust me, this is coffee, for example. We'll just say that. All right. Okay. So these are just groups of carbon and hydrogen in hydrogen atoms that aren't necessarily reactive. We give them the general abbreviation of R because these guys here don't really react. What reacts mostly is the functional groups. Here's something that people call a functional group, and I am sort of, I guess, okay with it, I guess, but whatever. So here's one. Here's something. All right. Phenyl and benzyl. Phenyl group is a benzene ring attached to a carbon attached to something. That is a phenyl group, not a benzene group. A benzene, when it's attached to another thing, could be I'm just saying it could be a phenyl group, right? It's just a benzene attached to something. It is abbreviated. It's either drawn out or drawn with the cyclohexyl with the circle in it, or you can draw the condensed form, the condensed formula, or pH for phenyl, or that little symbol there, which I believe is called Phi. I believe it's called Phi. I get Phi and Psi confused all the time, but I think that's Phi. And the other thing underneath that is the benzyl group. Now notice how your benzyl group and your phenyl group look similar, but they're not the same. The benzyl group is, so if we're talking about just a phenyl group, we're talking about just a benzene ring attached to God knows what. If we're talking about the benzyl group, the blue one underneath it, it's going to be the benzene ring plus a CH2 group attached to God knows what. So it's benzene, CH2, then whatever you want to do. And that can be drawn out as what you've seen there, or what you see there on the next side over there, which is the ring with the circle in the middle of it, or BN, or the condensed formula, that kind of thing. All right, here's probably your simplest functional groups, right? And we're gonna loop in a few different things with this concept. All right, the one thing that we're gonna loop into it is positionality or substitution. All right, so there is a chlorine, bromine, or iodine attached to your parent backbone. So Rx up there at the top, X could be fluorine, chlorine, bromine, or iodine. Those halides, they are reactive because you can eliminate them, you can substitute them, you can do lots of things to them, and we will be using that functionality for the entirety of this course. All right, and so that's something. That's probably your simplest functionality, which is very good to learn. All right, but let's talk about how we can connect these things to the carbon, the carbon backbones, right? So the lower right, you have a carbon that's being pointed to, right, by that pink arrow there, and that carbon there it has attached to it another carbon from there on the right, I'm sorry, on the left, and there's two other things on there. There's two hydrogens on there, then there's a chlorine on there. So that carbon that the chlorine's attached to is only attached to one other carbon. All right, so that pink dot is a carbon. That pink dot is only attached, that pink dot, which is a carbon, is only attached to one other carbon. Since that is the case, we call that one a primary carbon, and the thing on it, which is the chlorine, is a primary chloride. All right. So not only is the carbon primary, but the attachment of functionality is also a primary as well. All right. So again, there's nothing to it. It's as easy as it looks, right? You look at that dot, right? You look at the dot in question and you say how many carbons are attached to that carbon. If you say one, then it's a primary carbon. All right. Moving on to the middle. That vermilion or orangey dot in the middle is a carbon. That carbon is attached. That carbon itself is attached to two other carbons, right? And when that happens, you call that one a secondary carbon. And that bromine, which is, if it's attached to a secondary carbon, is called a secondary bromide, right? Pretty good, pretty easy, pretty straightforward, right? And then thirdly, going off to on the right side of the slide here, you have a carbon, that blue dot, that's attached to three other carbons, and that is a tertiary carbon. And then iodine that's attached to a tertiary carbon is a tertiary iodide. All right, primary chloride, secondary bromide, tertiary iodide, okay? Because each of the carbons are attached to as many carbons as is noted in the name. So that primary carbon is a carbon that is attached to only one carbon. That secondary carbon is attached to two carbons. You know, in the middle there, it's on the upper and the left side, in the upper and the lower left. And that tertiary carbon that has the iodine on it is attached to three carbons. Okay. All right. And so here is two things that are sort of related. And right now, it seems like there's a whole bunch of crap that's being thrown at you in terms of nomenclature. You don't have to necessarily remember. You have to remember, okay, you have to remember this for the exam. You have to know it for the exam. Primary, secondary, tertiary, you know, that kind of thing. Double, you know, it's simple functionality that we'll talk about, and that kind of stuff. But this is stuff that we'll keep on sort of going over, and we'll continue to build on your knowledge. Here you have a bromide here that's on an alkene group. So there's your carbon-carbon double bond right there, and you have a bromine attached to that. If you have a functional group that is attached directly to a double bonded species, that bromide there is called an alkenyl. An alkenyl bromide, right? Specifically an ethynyl, because that's ethyl is for the two carbons there. But an alkenyl is an alkene carbon. So this guy here is an alkenyl bromide, but it's really an ethynyl bromide because of ethene here. Moving down there, a benzene ring attached to a halide of some sort is not like a phenyl chloride or a benzenyl or whatever. None of that crap. It's called an aryl. It's an aryl group. Now it's super frustrating. It's super confusing right now. I know, right? Because right now I just said, you know, before so it was benzene, and now it's all of a sudden it's a phenyl, and then all of a sudden now it's a goddamn aryl group. I know. I'm feeling you. I understand. That it's just you're learning the name. It's like learning the names of your friends in class, except these friends here you don't necessarily want to spend time with or bum money from, right? So it's just what it is. Whenever you have something that's attached directly to a benzene ring, depending on what you're talking about, it could be an aryl group. Like this guy here is an aryl chloride. Aryl comes from arene, and arene is the general term for benzenes. So that's where these things come from. It's a lot of crap thrown at you right at the very beginning, and it's just what it is, okay? Just don't let it go. Don't get frustrated. Don't let it get the best of you. As soon as it pisses you off, it wins, and it's trying to piss you off, okay? So don't let it do that. Don't let it do that, okay? Alcohols and phenols. Okay, so alcohols, ROH. Notice the R stands for your alkane group. You know, we don't care about it. We just say R group, whatever it is. But what's important here is your OH group. This is a really important functionality group, right? So this is as important as, you know, your halides. Look at your primary alcohol, your secondary alcohol, and your tertiary alcohol. And that first alcohol is, I'm sorry about the yawning. I don't sleep well at all, and I'm sort of like a weird insomniac, and that's just sort of why that's why reality is sort of always questionable for me. I don't know if I'm dreaming or awake or what's actually happening at any certain point, but thank God I can do organic chem, right? That's the good part, right? But I sleep like shit, so that's just how it is. But so here's alcohols and phenols. So the first one here is ethanol. Ethanol, again, is a popular beverage with you children. You love to drink it and then prance around being joyous. And that's all well and good. But, you know, it's just the same. This primary alcohol here is the same exact thing as a primary chloride. It is, you know, if this chlorine here is attached to a carbon, that's attached to only one other carbon, this alcohol is attached to a carbon that's only attached to one other carbon. The same thing with the secondary alcohol. That alcohol is attached to that central carbon, and that central carbon only is attached to two other carbons, right? So we're good, right? There's only two other carbons attached to that. Same thing with the tertiary. The tertiary alcohol is attached to a tertiary carbon. It's a tertiary carbon because it's attached to three other carbons, around it. That's all it is. And the aromatic, that aromatic alcohol here is called a phenol, and that phenol is an OH attached to directly to a benzene. How's that for another version of goddamn benzene? Now this bullshit's called phenol, right? It's called phenol, but you just said it was an aryl chloride, but you just said it was a phenyl, but you just said it was a goddamn benzene. Why benzene? Why? Make up your mind. I know. Just it is what it is. It's a phenol. Why? It's because listen to this. It's a mushed up word. It is a, what do you call it? It is a portmanteau. Portmanteau. You Francophiles, tell me if I'm saying that right. Portmanteau. A portmanteau is like two words smushed together to make a third word. Give me a good portmanteau. Why can't I think of one? Two words that when you combine them together make up a third word. Why can't I think of one right now? I can't think of one. I'll think of one later. But it's like, well, here, right? This phenol is a phenyl group and an alcohol. You take the first part from the phen and the last part of the OL from alcohol, and you make phenol. Phenol is a phenyl alcohol. That is your portmanteau, right? There's that, right? So there's that's why it's called a phenol. All right. And so alcohols can be viewed structurally in two ways: as a hydroxyl derivative of alkanes, or as an alkyl derivative of water. And that's a good point to make, but it is because they are, alcohols are so structurally similar to water, and that's why they are very miscible or mixable in water, and that's why you always can dilute more or less all of your alcohols in water. Thankfully, you can do that, and there's your beer and your vodka and your Cointreau, whatever the hell you guys are drinking these days. But it's just so there's it has similar bond angles, not the same. Your ethyl group around your ethyl alcohol is 109.5, but your water bond angles are 104.5. But notice how similar water is to the ethyl group, to the hydroxyl group in ethanol. It's only different by a few carbons, which is a big deal. Admittedly, it's a big deal. But in terms of like its properties, it's pretty structurally similar. And as a hydroxyl derivative, that just means that you can treat these things sort of like very strong bases when we get to that point. Hydroxyl groups are things that can help, that are Bronsted-Lowry bases that can help abstract protons. All right, and we'll talk about this, again in a whole bunch of detail. Ethers are any alkyl group, any two alkyl groups that can be the same or different, that are separated by an oxygen. So here you have an acyclic or a non-cyclic ether, and then you have a cyclic ether. In fact, right over there on the left side is an acyclic ether called diethyl ether. And diethyl ether was one of the first ethers that they used for anesthesia back in the good old bad old days of turn of the century surgery, which thankfully you should thank your lucky stars every day that we don't live like 100 years ago, because that shit was brutal, right? And that's when they used ether to like knock you out. It's not a wonderful, thankfully they had ether to knock you out, but ether, when you wake up from an ether dosage, you have this ridiculous headache, and you still probably have an infection in whatever leg they had to amputate anyway. So it was pretty evil. But so diethyl ether, that's a good, that was an anesthetic back in the day. All right, but it's any oxygen that is flanked by two hydrocarbon groups on either side, either by both as a ring or as a non-cyclized species. Amines are just alkanes that have an NH group on them or an NR group on them. But notice something strange about amines. So this guy here is an amine that has an NH2 group on it, right? NH2 group there, right? So look at your primary amine. Your primary amine is an NH2 group that is on your. It is only attached to one carbon. Look at now. This is going to be weird for you, okay? Because we talked about primary carbons, primary, secondary, and tertiary carbons. Let's talk about primary, secondary, and tertiary amines. Your central atom there is your nitrogen. Your nitrogen there is a primary nitrogen because that nitrogen means it's only attached to one other carbon. Your secondary amine is a nitrogen that is attached to two carbons. So nitrogen attached to two carbons is a secondary amine. Okay, and that tertiary nitrogen, that tertiary amine on the rightmost side is tertiary because it is attached at any one point to three carbons, to three carbon species. So it is a tertiary. All right, so it's the same thing as primary, secondary, and tertiary for a carbon, except it's with a nitrogen. But what does it look like we're forgetting there? It looks like we're forgetting the lone pair on that nitrogen. We didn't forget it. We just didn't draw it in because it is understood by those who are reasonably schooled in the art. And that's our excuse from being sloppy. It is just, we don't write all the details because, as we say, all puffed up. It's for those who are reasonably schooled in the art. Then we will know, of course, that because of our giant brains, we know that the lone pairs are there, right? That's sort of true. It's understood. But please be careful, okay? We're just learning, we're just learning all this stuff too. So don't just disregard it because you don't see it, right? Everything has to follow the octet rule at this point, okay? Underneath there, the cyclic amine, right? It is a what type of substitution is that cyclic amine? That is a secondary amine because that nitrogen is attached to two other carbons, right? Which that's a good thing to know. Right, and so you have that, and cyclic amines could be the same thing as a cyclic ether, just like we saw before. Just a cyclic ether is over there. It's a nitrogen that's in between, two alkyl groups. But notice that like hydrocarbons, you have to have a complement of hydrogens around them. But the complements of hydrogen around an amine is not the same as the complement of hydrogens for a carbon. The carbon full complement of hydrogen is four hydrogens around a carbon. The full complement of hydrogens around an amine are only three because you never protonate, you never add a hydrogen to that last lone pair. Because if you do that, then that nitrogen ends up being electron deficient, ends up being a positive charge, and that is not necessarily, not that's not favorable, but it's not a lowest energy species. All right, and right next to it is the aromatic amine that is stuck in benzene, and that is called pyridine. 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 Pyridine is a thing that you could, I think, buy at Home Depot or something. It is a base that it's not too strong, but it will absorb a good proton. Right, and that amine in pyridine also has a lone pair. That lone pair is sitting right on that nitrogen. Here's a little exercise for you. At this point here, you know enough to draw out the electronic structure of pyridine. Why don't you try drawing all the orbitals associated with all the overlaps with pyridine and tell me where that lone pair on that nitrogen has to be. It has to be in a certain place, right? It has to be in a certain orbital, and there's only one orbital that it could be in. Why don't you draw it out for me, and we'll talk about it during discussion. I'd love to know what your answers are. Aldehydes and ketones comprise a gigantic, and now oh wait a minute, here's something. Here's a portmanteau, ginormous. I hate that word. I never use it because it's ridiculous, but that's a portmanteau, gigantic and enormous. Ginormous, terrible word, but good portmanteau. All right, there's that. See, I knew I would come up with a French. All right, anyway, so aldehydes and ketones. Aldehydes are a carbon double bonded oxygen species that on one side of the carbon is an alkyl group and on the other side is a hydrogen. All right, just look at the just look at the structures here. Ketones are just like aldehydes, except they don't have a hydrogen on one side. They are in the middle of a carbon chain something or other, right? So they have one side carbon, a carbon double bond oxygen, and on the other side they have some other sort of carbonaceous species, another carbon species there. And those aldehydes and ketones. So aldehydes are ketones that are on the edges or on the end of a molecule that can have a hydrogen on them, and ketones are towards the middle of a molecule that has a chain. Okay, so or a ring. Okay, so if you look at down here on the lowest line there, right, you have ethanol. You have a CH3, CHO. That first one there is an aldehyde. That's called ethanol. Again, that's the sour taste in yogurt. Next to that is acetone, CH3, C double bond O, CH3, and that is acetone, and that used to be the active ingredient in nail polish remover. All right, not anymore. Now they use ethyl acetate. And here is a longer sort of generic random molecule, which doesn't make any sense really. It's just showing you the differences between a ketone, which cannot be on the end of a molecule, and an aldehyde, which has to be on the end of a molecule. That's just how it works. All right. And here are some various forms of ketone containing things. Ketone containing things, or another word for ketone. Another general word for the carbon double bond oxygen functionality in an aldehyde and ketone is also called a carbonyl. Carbonyl, CARBONYL, and that is a generic that's a generic aldehyde or a generic ketone. But carboxylic acids, esters, and amides are generic carbonyl containing functional groups. So, for example, the upper right over here, right, you have a carboxylic acid, right, and that is a carbonyl that is also attached to it on one side of an R group, so alkane, but on the other side it's attached to an alcohol group, and that is a carboxylic acid, right? So it's a carbonyl group there attached to an OH group. An ester group right next to it is a carbonyl group that has an OR group on it, so it's sort of like an ether, but it's not really an ether at all, but pretty reactive, and we will go over how that is reactive later on. But that's an ester, right? Next one here is called acid. Pardon me. An acid chloride. An acid chloride. That's a carbonyl containing species that has a chlorine on it. We can also have an acid bromide or an acid iodide or an acid fluoride too. And that guy there is the carbonyl with the chlorine attached to it. An amide is like an aldehyde, like a carbonyl containing thing, but with an amine on it. But it's not an amine and it's not an aldehyde, so it's a little bit of both. It's an amide. And last but not least, definitely, is something called an acid anhydride, and it's very closely related to the acid chloride. And an acid anhydride is, if you can imagine, taking two carboxylic acids and smushing them together where the two OHs crash into each other and one OH leaves. That's how you make an acid anhydride. That means a carboxylic acid, when that you've combined together, that water has left, and once water leaves, then you end up forming, that anhydride, which is like two acetones, like two aldehydes, like made from an ether, like that kind of thing too. But it's its own thing. It's called acid anhydride, and it's extremely reactive. All right. Let's just stop there for the day. That's good enough, right? 30 slides in. We'll finish up this guy here tomorrow, and that'll be it for today. So thanks for your time and attention, folks. Hope you enjoyed the screencast. Sorry about all the yawning. I'm exhausted. It's because I have a fevered brain, and I can't stop thinking of things, and it gets hard to sleep when you have lots of activity and lots of people in your head. So that's how that is. But enjoy? Question mark? Eat something, drink something, do something. But you can't do anything but eat, move your bowels, and study. That's it. You gotta just because this is summer. It's crazy. You have no time for anything. You have no time to hear me blathering on. So I will leave you to those things. All right. Have a good day, folks. Thanks for watching. Later.